today. So let's see, we're live, folks. So as I was saying, I will discuss today. No, sir, no. So there's one more week. The last week we are going to review for the final. So this is not the last week. This is the week when we take the test, and then there's going to be one more week after that. Folks, as I was saying, any other questions before I get started here? All right. So as I was saying, the volumes is our main topic today, and let me quickly review these volumes for everybody. So let's see what kind of volumes we're talking about. So last time I was explaining that we're looking at volumes obtained this way. This is the y-axis, and this is the x-axis. And actually, you know what? So let me just do these straight lines because I have the option here. So come on, straight line. Okay, so there's a straight line here, and there's another straight line over here. There we go, folks. So we got that, and that's the x-axis, and that's the y-axis, and this is the curve that we are going to rotate. Doesn't have to stick to the y-axis. Could be anywhere, maybe. Yeah. Well, there we go. So I have two vertical lines here, A and B, and I'm rotating, and I wonder what happens when I rotate this piece of area here. So when I rotate, folks, you get something like this. All right, so this is a solid in space that you're getting. So when you rotate, you get something like that, and there we go. So there's this thing. And you get this solid in space, folks, and this looks like let's see, looks like a let's see, what kind of shape is that? Like a drum, for example. So when you rotate that in space, you rotate about the x-axis, and the volume of this thing is going to be so the volume is going to be calculated. This is y equals f of x here. And again, we consider the area above the x-axis. The volume is the integral from a to b of pi times f squared of x dx. So what do we do here? So simply, folks, instead of saying pi f of x, which would be for the area, we do pi times f squared because, as we said last time, f squared, that represents the radius of a vertical section. So if you chop down a vertical section, you get a circle, a disk that has an area of pi times r squared, and r being the radius, that is this f of x plays the role of the radius. So this is the simple formula that I want everybody to remember for the final. It's not going to be on this coming test. Because again, I don't want to mix up volumes with other things before that. Those things are more important. Volumes, you'll see them again in calculus 3, but these things before volumes, substitutions, fundamental theorem of calculus, etc., and antiderivatives, you will not see them in calculus 2 reviewed. So maybe the instructor might be willing to review them. But I would doubt so. So in most cases, most instructors would assume these were really well understood, and you should be able to apply these yet again in calculus 2. So we're talking about volumes now, right? So this is not part for the test, but I want you to for the coming test, for the final. So I want you to all remember this formula. So this is absolutely the formula that you want to remember from this last part of the semester. And then it's easy, really easy to apply it, whether you do it by hand by calculating antiderivatives or by using Desmos, which is a very useful tool. I don't really care. So as long as you are able to set up the integral, assuming that you already know how to do antiderivatives and such, this should be a piece of cake. So I'm pretty confident that you're able to set this up and you got a good performance on the test on test 3, then you pretty much know how to do this. All right. So the problems that I'm going to do are applications of this formula. We did one last time. We're going to do a bunch of them this time around. So let's do this one here, number 2 of section 5.2. And we're going to do only problems today. So this is going to be our topic today, calculating integrals like this. We're going to start with some standard one, more straightforward ones, and I'm going to show you some slightly more sophisticated example towards the end of the hour. Well, I'm not going to include those on a test, but again, you might need to know them, and you might run into those situations in physics or chemistry, because sometimes you have to calculate volumes there, and it's useful, especially when you study thermodynamics and things like that. So if any of you takes that class, then that's going to be one of the topics. So here we go. We have a function called y equals 1 over x. And we say here, so take y equals 0, take y equals x equals 1. I'm sorry. So there's x equals 1. And takes x equals 4. And the good thing about this problem says here, rotate this about the x-axis. So the good thing about this problem is I really don't have to picture anything because I have everything I need. So basically, folks, look at this. X equals 1 and x equals 4. These tell me the bounds for the integration. So I can just say simply here, volume equals integral from 1 to 4. The curve that's on top is this one here. The curves that at the bottom is this one here. So I can say, because this is the x-axis, by the way, y equals 0, right? So when you go with displacement 0 in the y direction, that means you're not going away from the x-axis. So this is going to be pi times, and f of x is this guy here, 1 over x. So 1 over x squared dx, and that's going to be equal to, so we are going to calculate this one, integral from 1 to 4, pi times x to the negative 2 dx. All right, so this is the integral that I want to evaluate. Now, x to the negative 2 simply is, if you want to evaluate that particular integral, so 1 second, folks, that's simply an antiderivative, so pi x to the negative 2 dx. So remember, this is the fundamental theorem calculus, what we're doing right now. So this is going to be pi times the antiderivative of x to the negative 2 is going to be x to the negative 1 times 1 over negative 1. I'm going to put that minus sign in front here. So it's minus pi x to the negative 1. So this guy that I want to calculate is minus pi times 4 to the negative 1 minus, that's one thing, minus pi times 1 to the negative 1. So that is going to be equal to negative pi over 4 plus pi, and that's going to be 3 pi over 4 for the final answer. All right, folks. This is as easy as a calculation is. Now, if you wonder what this picture looks like, I am going to quickly sketch it here for you. I don't need Desmos. Really, this is a really simple curve here, folks. There we go. So these are the lines. And I am going to say, I'm not sure if you see that. Do you see that? Folks, let me know if you see this part here, because it seems like it's covered by this other part on my screen for whatever reason. So I'm drawing the sketch here. Okay, perfect, thank you. So there we go. So folks, the curve y equals 1 over x. This one is the usual hyperbola. It looks like that. And x equals 1 would be someplace here. Let's say x equals 1, and x equals 4 will be someplace here, let's say. All right, so this is the thing, this area, this is the one that we're rotating about the x-axis. Now, when you rotate, you will get something like this. All right, so rotate above the x-axis, you will get something like this, folks. So you will get this thing. So you will get this solid over here, which really looks like a trumpet, if you want. So you're calculating the volume of this particular trumpet. That's the calculation that you're doing there. Again, you didn't need the shape of a picture here, really, because we have it already set up in the problem. So there's nothing really intelligent that I would have to do there, other than just take the formula at the top and apply it to this particular situation. So just recognize, identify, practically identify A, B, and F according to the given data here. All right, so that's problem 2. And I'm done with this problem here. I am going to do something else. So we're going to go slowly here, and we're going to take a few more problems to understand the topic here very well, and then we'll move on to something else. So there we go. There's another function here that's also interesting. Let's do this one, problem number 4 of section 5.2. All right, so problem number 4, again, y equals the square root of 25 minus x squared, y equals 0, x equals 2, and x equals 4. All right, so this is yet another function that's very interesting. In fact, this, folks, is a circle if you graph it. I'm not going to worry about it because it's not needed. So if you want to calculate the volume, what you simply have to do is say an integral from 2 to 4 of, and then you're going to say pi times f of x, which is this guy here, squared. So will be square root of 25 minus x squared dx. And if you do that, then you get an integral from 2 to 4, and then the square here is 25 minus x squared dx. All right. So this thing here is yet again a problem, a simple problem of antiderivatives, which I hope so. So again, I'm doing this also as practice, folks, for the fundamental theorem of calculus. We're applying this over and over again, and I hope this really sticks in your head. And when you move on to, so if you move on to calculus 2, you remember these things, because you'll have to do this over and over again there as well. So this type of integral, again, you calculate the antiderivative separately. Some people say in colloquial, language, we just drop the integration bounds. we don't lose them, but we just, so that's the equivalent to saying, calculate the antiderivative of 25 minus x squared dx, which is 25x minus 1/3 x cubed. So this is the antiderivative. All right, this is the thing that you're going to take and substitute in here. Now, because I don't have room there, I'm going to take the integral. I'm going to write it down here. So what I have to do, I have to take this function and substitute in 4 first. So 25 times 4 minus 1/3 times 4 cubed. And then substitute in 2. So 25 times 2 minus 1/3 times 2 cubed. So this is going to be, folks, all right, so this is 100 minus 50. So that's going to be 50 minus 4 cubed is 64 over 3. And then it's going to be plus over here, minus is plus, plus 8 over 3. So 64, negative 64 plus 8 is negative 56. So negative 56 over 3. And this number is, if you want to calculate this out, this is, let's see, boy, 50, that's times 3 is 150, minus 56 is going to be 94 over 3 or something like that. So I hope I did that right in my head. So let's see, 150 minus, all right, yes, yes it is. So this would be the final answer. Now, if you want, again, you can calculate this with decimals and you'll probably confirm this result. All right, so folks, again, very easy problem. You see that the important part is to be able to set it up properly. Pi times f of x squared dx. So that is problem 4. And I hope my message has gotten across. I'm going to do one more question. This is a bit more challenging. It's going to be a bit more challenging. So number 7, I'm going to do a few more challenging problems. And then we'll go back and we'll see, so number 7 of section 5.2, we'll go back and we'll see what happens when we rotate above the y-axis. So number 7, y equals x squared, and y equals, I'm sorry, oh boy, my eyes aren't, all right, y equals x cubed actually. And y equals x, that's the second thing, and we want x to be greater than or equal to 0 above the x-axis. All right, so this is number 7, and let's you know what, I don't like the way I wrote that. Okay, so y, there we go, that's slightly better. This is a type of problem where you're going to have to be a little more careful. So does not come with the bounds. So we have to figure out the bounds ourselves. All right, so now comes the place where Desmos is really useful. And I'm going to pull up Desmos. All right, so I'm going to pull up Desmos and I am going to do the following thing. All right, so I'm going to share with you, share Desmos. All right, so there we go. I think you actually see it right now. Y equals x cubed. There we go. There's Desmos. And the other function was y equals x. And we want x to be greater than or equal to 0. So basically, that's the area between these two curves that are rotating above the x-axis. Now, what is that going to look like? Well, that's going to look like these, folks. So when you rotate the line above the x-axis, the line y equals x, you get an ice cream cone. Now, imagine that out of this ice cream cone, you remove ice cream in the shape of like some sort of a funnel, like a the shape of let's say a trumpet. So you remove it, but you leave some ice cream on the side of the cone. That's the thing that you're obtaining there. And the important thing here is that we write the integral properly. Now, how do we get the stuff that's obtained by rotating the thing between two curves? Well, let's look at that on the whiteboard. So on the whiteboard, so here we go. So I'm going to do this by hand without that tool. All right. So let's say we rotate this line. What happens when we rotate this line? Well, we get this solid cone, right? So when you rotate the line, but then you also rotate the curve, this one, and when you rotate this one, you also get a solid. So you get another solid, but this solid is in the shape of in the shape of a trumpet, if you want. If you've seen those trumpet kind of arched nicely, that's the shape that you're getting there. And the thing is here that you're rotating this part, and you get the inside of a trumpet, but then that's going to be subtracted from the part that you're rotating when you rotate the outside curve. So over here, the formula will be a little trickier. So first of all, we need to remember that this is 0 and this point here, this end point here is 1, because we saw that the curve ends at the point 1, comma 1. Let me share that with you quickly here. So look, folks, this is 1, comma 1. This is the end point here. So 1 on the x-axis, yeah. And we're going to set the integral from 0 to 1. But now remember, you subtract the inside volume from the outside volume. So the outside volume is pi times the outside curve, which was this one, x squared, minus pi times, and then the inside volume will be x cubed squared. So that's going to be dx. That is the situation that is there. And when you subtract these two, what you're getting is the integral from 0 to 1, pi times x squared minus pi times x to the 6th dx. This is a thing that you are subtracting. And this is the volume that you're gonna get. So it's the leftover here, which I'm gonna color with red here. This part here, this part here. So you know it has thickness, right? So it's all around. Of course, it's all around here. So it's the ice cream that's left stuck to the walls of that ice cream cone. So folks, what I'm saying here is that we need to calculate this integral, the difference of volumes, not just the volume, right? All right, so if my message got across here clearly, then this is going to be yet another easy calculation at this point in time. So the point is, be careful when you set up the integral. At this point in time, the antiderivative pi x squared minus pi x to the 6th dx is going to be pi over 3x cubed minus pi over 7 times x to the 7. So that's the thing there. And this is going to be the thing that I am going to estimate between 0 and 1. So pi over 3 at 1, you get minus pi over 7, right? So this is at 1. And then at 0, you get 0. So 0, 0. So minus 0, and that's 7 pi minus 3 pi, it's 4 pi over 21. This is going to be the calculation, and that's the answer for this particular problem. But again, be careful. So when he says rotate the area between the two curves, because that's what he says in the problem, you want to be careful to subtract the volumes. So not just the volume, subtract, right? So that's what you want to pay. That's one aspect you want to pay attention to. Okay, and I'm gonna do so. So we did a bunch of problems here. We did let's see, 3 problems and a bit of a review there. All right, so I'm gonna go and I'm gonna do another problem. This time I'm gonna do problem 8, and you will know very well how to do problem 8 at this point in time, because problem 8 really is it's just a repetition of a previous part. So y equals, we got y equals 6 minus x squared, and also y equals 2 in problem 8, and you want to rotate above the x-axis. All right, so let's see, what does this look like? Now, fortunately, I know what this looks like. I can easily tell what the graph is here. Well, I'll show you quickly here what the graph looks like. So the graph looks like this, folks. Okay, so 6 minus x squared, that's going to be negative x squared up 6 units. So it's going to look something like this. And then y equals 2 is going to look something like this. Y equals 2. and that's going to be 2, and that's going to be that. So this is the area between the two curves. And this is what we want to spin about the x-axis. So we spin this thing about the x-axis. What do we get? Well, we get the following shape. So the shape that we get here is something like this, and something like this, and then something like this. So this is the thing that we get, and what it is, well, it's the so you have this bucket, and you drill a cylindrical hole in the middle of a bucket. So let's say your mom's flower pot, right? So a bowl basically, and you make a hole in the middle of that bowl. I don't say that you should do that, but that's what this one looks like, and then you drill a cylindrical hole. So that's a thing that's left. It really so it has thickness, this thing, right? So we want to calculate this thickness. Really, it's on the sides of the cylinder. So putting some thickness on the sides of the cylinder. So now the volume is equal to, and right now here, folks, let's figure out. So this is 2 here. What's this corner here? We can figure out just by looking at the equation. This equation here is 6 minus x squared. And now if I remember, so I want y to be 2, right? So when y is 2 and is also 6 minus x squared, if you set these two equal, you can look in decimals, of course, and you can figure out this corner here. But you can easily do 2 equals 6 minus x squared. And then if you solve for x, you will see that x is also 2. So this point here is really 2 comma 2. Look here, so 6 minus 2 squared is also going to be 2. So this point being 2, it means that the left and the right bound are at 0 and 2. And what we're going to do, pi times that one squared, 6 minus x squared squared, minus pi times x squared squared. Pi times, I'm sorry, not x squared, minus 2. So pi times 2 squared, because this is the second function. So first function, second function, top and bottom. All right, so this is what we want to integrate. And really this boils down to saying, without those squares, pi times, now 6 minus x squared squared is 36 minus 12x squared plus x to the 4. If you remember the perfect square formula, folks, which is again a plus b squared equals a squared. So let me write it down here. A plus b squared, a squared plus b squared plus 2ab. This is the case here when you do 6 plus negative x squared and you calculate, it's going to give you this. If you don't remember, just do it by hand, folks. Do distribute the powers of x and such and do by hand, and you'll get this thing minus 4 pi. This is going to be dx. All right, now this is integral from 0 to pi. 36 pi minus 4 pi is 32 pi. Then minus 12 pi x squared plus pi x to the 4 dx. So folks, the antiderivative that we're looking at here is this one, 32 pi minus 12 pi x squared plus pi x to the 4. And that is going to be equal to 32 pi x minus 12 pi x squared is 12 pi times the antiderivative times 1/3 x. So that's going to be 4 pi x cubed, 1/3 x cubed, I should have said, plus 4 over 5, pi over 5 x to the 5th. All right, folks, so this is the thing, and we're going to do this from 0 to pi. The good thing is that when you plug in 0, you get 0, 0, 0, so you don't have to worry about that. You just plug in pi. So Now, why did I say pi? So I'm sorry, folks. It should have been 2 here. Really, just copied the wrong thing. So my apologies. This number should be 2. And this number here should be 2 as well. All right, so sorry about it. The bounds were 0 and 2. So we really plug in 0 and 2. So that's going to be in this formula. So that's going to be 32 pi times 2, which is, let's say, directly 64. Oops, sorry about that. So let's say 64 pi minus 4 pi times 2 cubed times 8, which is minus 32 pi plus pi over 5 times 2 to the 5th, which is 32. So 32 pi over 5. So that's 64 minus 32, 32 plus 32 over 5. That's so it's 32 pi plus, now 32 over 5 is 6 and 2/5 pi. So that's if you calculate carefully, it's going to be okay. So 38 pi and 2/3. So 38 and 2/3 pi. So this is the number here. It's a larger number. When I multiply, I even, well, that's 3 times 8, 24. 6 plus 2, 86 over 3 pi, 86 pi over 3 if you want. So that's the final answer for this particular problem. And I hope my message got across with these things again. So the only difference between the second style of problem that we did today here and the first one is that the first one says, okay, so rotate this above the x-axis and see what the volume is. This one, you rotate a region between 2 curves, so you have to subtract the interior one from the exterior one. So that's kind of the only difference. But the formula doesn't change, so it's just a difference of those formulas. All right, and finally, today I'm going to do another problem that is slightly different from the ones we did up to this point, in the sense that we rotate things above the y-axis. So number 9 of section 5.2. So we got this y squared equals x and x equals 2y, and we rotate above the y-axis. And as I told you, so I could represent this picture, but I'm not. So as I told you, when you want to rotate things above the y-axis or calculate integrals in the y direction, what you could do, and I recommend students to do this, to change the letters x and y if convenient. So whenever you calculate something like volume or area or something like that, change the letters x and y. Those notions don't change because this is what's called an isometry in math. So it's something that preserves the lengths, volumes, areas, and such. So change the letters x and y. Then the first equation becomes, and I'm going to write that in red. Oops, come on. Becomes. Oops. Let's do this. Sorry about that, folks. Let's write x squared equals y. The second equation becomes y equals 2x. And we rotate, so we rewrite the problem here. So rotate about the x-axis. We said that we change the letters x and y. So look here. So they're all changed in the formulas here. So this is going to become a very simple calculation, because what I have here is something I can easily graph. Notice that I can rewrite this as y equals x squared, which is a parabola. So if I do the red thing, so this is the rotated thing, y equals x squared looks like this. Y equals 2x is something like that. I have the area between 2 curves. I know which one is on top. This one is on top. This one is at the bottom, y equals x squared. And they will intersect somewhere. And this point of intersection you can do with Desmos. I'm not going to do because I don't have time to move back and forth between the two. This point is going to be 2 over here, because if I look 2x and x squared equal, well, that should be x equals 2. And this is 0. So when I set up the integral, I can calculate the volume between the volume obtained by rotating this thing, like I did in one of the previous problems. You can recognize the exact same style. So integral from 0 to 2, and over here you're gonna say the pi times the top function squared 2x squared minus pi times the bottom function squared, which is x squared dx. And that is going to be equal to for the integral 0 to 2 for pi x squared minus pi x to the 4 dx. So so this is one of the things that we calculate. And the second thing that I want to say here, well, the antiderivative, again, very quickly here, 4 pi x squared minus pi x to the 4 dx is going to be 4 pi over 3x cubed minus pi over 5x to the 5th. Substituting here, the numbers are, again, so substitute this formula, 0 is going to give you 0, so I only have to worry about 2, 4 pi over 3 times 8 minus pi over 5 times 2 to the 5th is 32. So 32 pi over 3 minus this here minus, so it's 32, let's factor out the 32, and pi, and it's going to be 1/3 minus 1/5. And this number is 5 minus 3, 2 over, so it's 64 pi over 15. So this is going to be the final answer. The red problem is again, the difference is rotation about the y-axis. So that's the main difference between this problem and the previous problems. Now, the good news is I told you I'm not going to put a rotation above the y-axis, because I'm pretty confident that everybody can switch the letters if they want to. In practice, you know, this is one particular type of problems of many other types of problems that could be asked about volumes. More on that in Calculus 3, most likely. So I am not going to worry about those too much. All right, folks. I am going to stop the recording here. If